Okay, welcome to Robotics 1. In today's class, we are going to start working out the problem and we will extend that using MATLAB. So in today's class, we will use MATLAB. Today's class again is super important. So very important lesson. So this is very important lesson. Now in the last class, what we did is we looked at the kinetic energies and potential energies of the robot. That robot had slender rods. So let me show you the kinematic diagram. This is how the robot was set up in last class. So we had a rod here. Then there was a revolute joint here. And then there was another rod that was attached over here. So this is A1, which is the length of the first rod. And this is A2. Now, before we begin solving the problem, I want to be very clear about the area mass moment of inertias. And this is going to be super important. In the last class, we looked at the kinetic energies and the potential energies. So in the coordinate x0, y0, and z0, we derived the equations for kinetic energy and potential energy. This is theta 1. And let me set up the coordinate system for this guy, which is something like this. And x1, y1, z1. Now, we looked at the potential energies and kinetic energies. Let me write the most general expression. So the kinetic energy was written as 1/2 m1 vx1 square plus vy1 square plus vz1 square plus 1/2 I xx1 omega x1 square plus 1/2 I yy1 omega y1 square plus 1/2 I zz1 omega z1 square. This is for the first link. Continuing, for the second link, the mass is m2 and the potential kinetic energy is vx2 square plus vy2 square plus 1/2 vz2 square plus 1/2 I xx2 omega x2 square plus 1/2 I yy2 omega y2 square plus 1/2 I zz2 omega z2 square. Then we had the expression for the potential energy. Potential energy is plus m1 g1 pz1 plus m2. So this is just g, G is constant. P, Z, 2. Then we have the Lagrangian, which is L, which is the total kinetic energy, and V, which is T minus V. Now, what we are going to do in today's lesson is we are going to solve this big expression using MATLAB. But before I begin, I have to emphasize on key concepts. Please note there is IXX, there is IYY, there is IZZ for link 1. There is IXX2, IYY2, IZZ2 for link 2. Now, for a rectangular bar, I just want to write this down just for our own reference. I gave the expression for IXX, IYY, and IZZ. And if this is length L, this is height H, and if this is width W, then depending upon how you set up the coordinate system. So now I need to write this down very carefully. Please note that this is my coordinate system. This is how I'm setting the coordinate system. It has to be a right-hand coordinate system. This will be X. This will be X. This will be Y. This will be Z. We found out IXX is 1 by 12 M L square plus L square plus W square. Now IXX is 1 by 12 W square plus H square W square. IYY is nothing but 1 by 12 M L square plus W square, and IZZ is equal to 1 by 12 M H square plus L square. 1 by, oh yeah, this is not right. Just, yeah, Vx, that is how it is. Okay, so now the question is, please understand that the mass moment of inertia for a bar is represented its own coordinate system. And at this point, we have to find out, this is the key question. What is IXX1, IYY1, and IZZ1? Second question is, what is IXX2? What is IYY2? And what is IZZ2? And this is not a trivial question, because please try to understand how the coordinate systems are flipping. So we have to be super duper careful. But one thing I want you to note, and this is super important, all these angular velocities, all these translational velocities. So the terms here, the angular velocities and translational velocities are with respect to the zeroth frame. So all velocities are inertial velocities. Inertial means with respect to zeroth frame. In other words, if we want to find out IXX, IYY, IZZ, they should be with reference to the zeroth frame. That is super important. Ixx, Iyy, and Izz for individual rods, even though they may be oriented differently, they should be with respect to the zeroth frame. And when you construct a solid model using SolidWorks automatically takes care of this translation, and we will work out a problem. At that time, you will realize. Now, what I want to do is, I want to work out these inertias for this particular problem. And then we will move on to MATLAB and work out the problem. So let's start with this first rod. And I'm going to assume this is like a slender rod. And there is another rod, which is something like this. So this is the link 1. This is the link 2. This is link 1 and link 2. And the question is, I want to find out Ixx, Iyy, Izz for both the links. Please note, before we start, let's identify the coordinates for our zeroth frame. Why the zeroth frame is very important is because all our velocities are in the zeroth frame. So I have z0, I have x0, I have y0. So what I'm going to do is, for the sake of understanding, I'm going to locate the centroid of the first rod. I'm going to locate the centroid of the second rod, and then I'm going to redraw this frame. So I'm going to redraw this frame. I'm going to redraw this frame, the zeroth frame. And I'm going to write down again x0, y0, z0, x0, y0, z0. Now, the moment of inertias I'm going to find, and I will show you how to find it. This length is A1. This length is A1. This length is A2. This length is A2. And I'm going to assume the other dimensions like width and thickness of both the rods. Width and thickness is approximately 0. So my Ixx, so I'm going to write the equation for Ixx1. Ixx1 is going to be 1 by 12 m A1 square. Iyy1 is going to be 1 by 12 m A1 square. Izz1 is going to be 0. Next, Ixx2 is going to be 1 by 12 m A2 square. Iyy2 is going to be 1 by 12. So this is m1, m1, this is m2, m2, a2 square, and Izz, actually Ixx is going to be 0. Ixx is going to be 0. Izz is going to be 1 by 12 m2 a2 square. And the reason, because I'm assuming this dimension and this dimension to be 0. I'm assuming this dimension and this dimension to be 0 or very small compared to the length. This is called as the slender rod assumption. So we are assuming link 1 and link 2 be as slender rods. Everyone understood this? This is super important because whenever you are trying to solve the robot problem, if you look at, let's go a step back. When we are trying to find out the kinetic energy is with velocity. That velocity is expressed in the inertial coordinate frame or the zeroth coordinate frame. That's why when you take the mass moment of inertias, your coordinate frames should match. If they don't match, then you're not going to get correct answer. And that is something that you want to keep in mind. Everyone, any questions on how we found the mass moment of inertias? Now, from last class, if you look at the expressions that we have derived the expression for kinetic energy, we derived expressions for potential energy, and now what we are going to do is we are going to go to MATLAB. So I'm going to switch to MATLAB and show you how to work out this problem. So the coordinate of the second rod must match each other. I did not understand your question. What I'm trying to say here is, for finding out mass moment of inertias, find out the centroid of each link. Redraw the inertial frame or zeroth frame on the centroid and find out the mass moment of inertia the way I have shown over here. And that would be the correct mass moment of inertia. So you will duplicate the zeroth frame on link 1 and link 2. All right. If we are comfortable with this, now what I want you to do is I want you to open R90R Robot MATLAB script. And this script we worked on last week. And the zip file with MATLAB script and the Euler-Lagrange.m is uploaded in Canvas. So please open that. And last time we solved the same problem, except we had masses M1 and M2 at the end. So now we are going to start with the same script, and then we are going to modify the script so that we can solve this problem. So everyone, now let's go to, I'm gonna start sharing my screen with MATLAB. So you should be able to see my MATLAB screen. Please note this code This code is the same code that we ran when the masses were at the end. Now we need to modify this code. So please understand, there is kinetic energy of the first mass, there is kinetic energy of the second mass, there is potential energy of the first mass, and the potential energy of the second mass. So what I'm going to do is, here first we already found out the mass moment of inertias, so I'm going to type those in. I'm going to say I xx1 is equal to 1 by 12 multiplied by m1 multiplied by a1 square. This is the mass moment of inertia of the first link in x direction. I yy1 is equal to 1 by 12 times m1 times a1 square, and izz1 is equal to 0. So this is the mass moment of inertia, mass moment of inertia of first link. Now we have to find out mass moment of inertia of the second link. So mass moment of inertia of the second link, Ixx2 is 0. Iyy2 is 1 by 12 m2 a2 square, and Izz2 is equal to 1 by 12 . So this becomes. Any questions at this point? Now what I need to do is, I need to find out the kinetic energy in translation. I need to find out the kinetic energy in rotation. So first, I'm going to find out kinetic energy in translation for mass 1. Kinetic energy, I will say T1 T. This is KE in translation for mass M1. T1T, and we already have the expressions for the velocity that we derived in last class, and I'm going to write that equation down over here, and you can quickly check if this equation is the same equation that we derived in last class. So this is Vx1 square. This is Vy1 square. And this is, oh, this is actually T1T. Okay, sorry, my bad. T1T is 0. T1T is 0. Yeah, I'll put that in the chart. On because translational velocity of the first mass is 0. T1 R is equal to IZZ1 0.5 multiplied by IZZ1 multiplied by TH1D square. Now please note IZZ1 is 0. So T1R is going to be 0. Please note IZZ1 is 0. So it's going to be 0. So this is kinetic energy for mass M1. T stands for translation. This is in translation. This is in rotation. Now let's look at kinetic energy for mass M2. This is T2T, which is the kinetic energy in translation. And I'm gonna write this expression down. Copy, paste. And I will copy and paste this expression in the chat window. And I want you to compare this expression to the expression that we derived in last class. So we derived the velocities. This is Vx2 square. You can see the square term here. This is Vx2 square. This is Vy2 square. Vy2 square. And I just found an error in this expression. It should be minus. This is Vy2 square. And then this is Vz2 square. So this is the expression. This is the expression. So I will, A2 and L2 are the same thing, yes. So I will send you the correct expression. In just a second, this is the correct expression. So I'm going to highlight once again. This is 1/2 mass. This is the Vx. That term is squared. This term is Vy. That term is squared. And this last term is Vz. And that term is squared. Now we need to find out T2R, and T2R is, you want to be very careful, is let's look at the kinetic energy for the first mass. I mean, the kinetic energy omega x2 is sine theta 1 theta 2 dot square. So this is going to be 1/2 times I xx2 multiplied by th1d so the first term is sine theta 1 theta 2 dot, so sine theta 1 theta 2 dot square plus 1/2 times I yy2 multiplied by minus cosine theta cosine theta 1 multiplied by theta 2 dot square, and the last term is 1/2 I zz2 multiplied by th1d square. So I will so here, so th2d square 1/2 izz th1d. So please note, this is omega x2 square omega y2 square omega z2 square. So you get T2R. Now let's look at the potential energy. Potential energy for mass M1 is V1 is equal to M1 G1. That mass is at distance A1 by 2. So this is going to be the potential energy of mass M1. Potential energy for mass M2 is going to be so this is the slender rod. And I will save as 90R slender rod. So this is the slender rod example. Now we have to find the Lagrangian. Lagrangian is T1T plus T1R plus T2T plus T2R. So I added all the kinetic energies. This is the kinetic energy of translation of the first mass. kinetic energy of the rotation of the first mass, kinetic energy of translation for the second mass, kinetic energy for the translation of for the rotation of the second mass, minus potential energy for the first mass, potential energy for the second mass. Now, once we have set up the Lagrangian, everything else, let's quickly go through it. Our states are theta 1 dot, theta 2 dot. There is no external force, so we have zeros because 2 degrees of freedom. Again, zeros, 2 degrees of freedom, that's why 2 zeros. R is equal to 0. No parameters. We would invoke the Euler-Lagrange equation. Pause, time span. I'm gonna supply some initial conditions and then I'm gonna plot the plots. And let's see if this code runs. It's gonna take some time. As you can see, MATLAB is busy. Now let me show you the plots that I get. This is the plot I got. Okay, I will drop the entire code in the chat. Here it goes. I think for some reason I will send it again. I don't think it's allowing me to copy the whole thing. Let me see. Yeah. Okay. Okay, just quickly, were you able to get the code working? Yeah, there is a cap on how much you can copy paste. So let me actually convert this code into 2 sections, and then that will be easier. Just a second here. First, this will be one section. So I'm gonna paste codes in sections. Copy, paste. This is the first section. Then I'm gonna paste the second section. And now you should be able to run the code. Okay, I'm looking at some responses in chat window. Were you able to get the plots? Okay, fantastic. So that is how you would solve the problem. Now, the next problem, before I start, let me ask you if there are any questions. Are there any questions at this point? So now the question is, how do we solve a complex problem from start to end using MATLAB? So let's look at an example, and I'm gonna go back to sharing my whiteboard. So you should be able to see my whiteboard now. Now the question is, if I have a problem, how do I start from very basics and then get all the way up to the dynamical solving dynamical equations of motion? So let me solve this problem. This is a slightly complex problem, but we have solved part of this problem already. So we have a revolute joint, then there is a prismatic joint, and then at the end of the prismatic joint there is another revolute joint, and at the end of the revolute joint you have an end effector. So now this, you have the first revolute joint, then you have the prismatic joint, then you have the revolute joint, and you have the end effector. Now please try to understand. Let's identify how the links are going to look like. So I'm going to assume again that the links are like slender rods. So the links are like slender rods, and to show the three-dimensional representation, it is like this. But one thing to note, that this is a prismatic joint. That means the length of this link is going to extend. Now we have to make some assumptions before we work out this problem, and I will discuss what assumptions in just a second. But let me specify the link lengths. So the first link length, A1, is a fixed link length. The second link length is D2. It's a joint variable. It can extend. And then we have the last link length, which is A3. So A1 and A3 are constants, and D2 changes. Now I'm gonna go with the same assumptions. I'm going to assume that the masses are located at the centroid of these links. So the mass M1 is located at the centroid of link 1, link 1, this is link 2, and this is link 3. Mass M2 is located at the centroid of link 2, and mass M3 is located at the centroid of link 3. Now what I want to tell you here is, we have worked out the forward kinematics for this problem. Forward kinematics is worked out in lecture 6. So this might be a good time just to go to Canvas, open lecture 6, and quickly go through the forward kinematics, all that we derived. And when we did the forward kinematics, we found out 0R1, we found out 0H1, we found out 1R2, we found out 0H2, we found out 2R3, and we found out 0H3. So all these homogeneous transformations we already found out. So what I'm going to do is I'm going to use that information to solve this problem. And the process that we are going to use, it's same as before. As a matter of fact, one thing I would like to tell you that we also found out the Jacobians. So Jacobians, and I need to specify over here omega x1, omega x2, I'm sorry, omega x1, omega y1, y1, omega z1, which is the angular velocity of the first link, is 0r0, 0, 0, theta 1 dot. For the second link, omega x2, omega y2, omega z2 is equal to 0r0, 0, 0, theta 1 dot plus 0r1, 0, 0, theta 2 dot. And here I want you to be very careful, super duper careful. Please look at the joint variable. There is no theta 2 dot because it's not a revolute joint. Joint number 2 is a prismatic joint. So joint number 2 is P, not R. That's why theta 2 dot is going to be 0. However, the contribution from the angular velocity of the first joint would still remain as part of the Jacobian equation. The next thing I want you to understand is the last part, omega x3, omega y3, omega z3. You are going to have 0r0, 0, 0, theta 1 dot plus 0r1, 0, 0, theta 2 dot plus 0r2, 0, 0, theta 2 dot. And here, once again, there is no theta 2 dot. So this term is going to be 0. And you are going to need omega x1, omega y1, omega z1. So these three terms, and these three terms are needed to find the rotational kinetic energy. And for translational kinetic energy, we need to find out Vx1, Vy1, Vz1, Vx2, Vy2, Vz2, Vx3, Vy3, Vz3. So all these need to be found out. And the way you have to proceed very systematically, in a very step-by-step approach to solve this problem. So what I'm going to do is, now everyone understood the process We will first solve the forward kinematics problem. From forward kinematics problem, we will find out the positions px1, py1, pz1, differentiate those, find out vx1, vy1, vz1. We will solve the forward kinematics problem. We will find px2, py2, pz2, and then find vx2, vy2, and vz2. Finally, we will solve the forward kinematics problem px3, py3, and pz3, and then find out px3, py3, and vz3. Then we will derive the Jacobian expressions, and from the Jacobians we are gonna get all the angular velocities, and later we are going to find out the potential energies for link 1, link 2, and link 3. And before I proceed, I just want to take a minute here and answer any questions that you may have regarding this problem, because your next quiz will include robots that will have 3 or more joints, and you will have to follow the same process. So before I proceed, any questions? Raise your hand and I will unmute you if you have any questions. All this is great. One thing you also need here is IXX, and I'm gonna use the second page. So check this out. You have one link, then you have another link, and you have one more link. So you are gonna need IXX1, IYY1, ICZ1. Then I will have IXX2, IYY2, IZZ2. And then I need IXX3, IYY3, and IZZ3. Then, yeah, the solution for the quiz, Asjad has the solution for the quiz, and then he can post those. That's not a problem. So the question is, how do you find out IXX1, IYY1, and IZZ1? Start with your base coordinate system. X0, Z0, Y0. Find out the centroids. Centroid of the first link is at the half of distance A1. Centroid of the second link is at half the distance D2. Centroid of the third link is at half the distance D3. Then replicate the coordinate system. So you're gonna have Y0, X0, Z0, X0, Y0, Z0, X0, Y0, Z naught. Now, well, I will answer the questions related, not related to the material that we are discussing right now at the end. So you can ask me questions, but let's go through this problem first. Why did Z and Y? Oh, yeah, I made a mistake. I made a mistake here. This should be X naught, Y naught, Z naught, X naught, Y naught, and Z naught. Okay, good catch. So you need to replicate the coordinate system, the zeroth frame, this zeroth frame at the CG of each link. And based on that, we need to find the moment of inertias. So I'm gonna write the moment of inertias, and we are going to assume a slender rod, which means the length dimension is the most predominant dimension. Other dimensions are 0. And when I do that, so I get the expression for IZZ as 0. I get the expression for IYY as 1 by 12 M1 A1 square IXX 1 by 12 M1 A1 square. Now here, this is X naught, so I get X22 at 0. I get 1 by 12 M2 D2 square 1 by 12 M2 D2 square. Here I get the same thing. This is 0, 1 by 12 M3 A3 square 1 by 12 M3 A3 square. So now I have these XX, YY, ZZs for link 1. So this is my link 1. This is my link 2. And this is my link 3. Now what I can do is I can go to MATLAB and try to work out the problem. So I'm going to start step by step, but please understand it's a 3 degree of freedom system. So I'm going to start, I'm going to say this is going to be my Rpr robot. So I'm going to switch my screen to MATLAB. So you should be able to see my MATLAB screen. So this is my example Rpr robot. And this Rpr robot, I have 6 variables. And these 6 variables are TH1, TH2, TH1, TH1D, D2, D2D, and T3 and TH3D. So theta 1 dot, D2, D2 dot, theta 3 and theta 3 dot. And I'm gonna specify all the constants, copy, and then I will write this over here. And I'm going to assume the mass of the link 1 is 0.1 kg, mass of the link 2 is 0.2 kg. L1, L2, they are not needed. So actually, but I just kept it. A1 and A3, these are the link lengths. They are 0.5. Now I'm gonna copy the homogeneous transformations that we derived in lecture 6. So we derived the homogeneous transformations for this problem in lecture 6. And I will get those homogeneous transformations directly. I will paste them over here. So this is nothing new. This is something what we did in the past, where H01 is the homogeneous transformation from 0 to 1. R01 is the rotation matrix 0 to 1. H12 is the homogeneous transformation from 1 to 2. R12 is the rotation matrix from frame 1 to frame 2. 2,3 is the homogeneous transformation from frame 2 to frame 3. And now we will find out all the homogeneous transformations. So copy, I'm gonna paste it over here. And I'm gonna work out this problem in sections. So what I'm gonna do now is I'm gonna paste this section into the chat window. So I'm gonna copy this whole section and paste it in the chat window. So that way you can directly copy and paste it. And before we begin, let's try to work out the problem. I will try to save this problem. This I'll call Rpr Robot. So run the first section, and then at the end, it should give you okay, A2 is not, A2 is actually 0. H2 3. Yeah, actually this is, there is an error here. I will just correct it. This is D2. So please make sure that you correct here. There's a typo in here. This is cosine theta T H23. Please see H23. Oh, this is A3. Sorry, this is A3. A3. This is A3. There is no A2 anywhere. So let me run this code. And once you run this code, you should have H01, H02, H03. So if you just type H01, if you type H02, H03, you should have the positions. Now let's look at for H01. This is PX1, this is PY1, and PZ1. PX1 is 0, Py1 is 0, Pz1 is 1/2. So what this tells me is the velocity of the first mass is going to be 0 because it's not changing. The velocity of the first mass is going to be 0. Let's look at the second H02. This is the Px2, this is Py2, and this is Pz2. Understand this is a prismatic joint, Px2, Py2, and Pz2. This is Pz3, Px3, Py3, and Pz3. So what we need to do is we need to take the derivatives of these and then find out the velocities. But the good news is for the first link, the kinetic energy in translation is 0. And since the rotational inertia in IZZ direction is 0, the rotational velocity is also 0. So we'll start with the velocities and kinetic energies, KEs. So kinetic energy for the first mass, kinetic energy in translation, kinetic energy in rotation. Kinetic energy for the second mass in translation is this, which comes from the derivative of Px2, Py2, and Pz2. Kinetic energy for the rotation of the second mass is this, which is 1/2 m2 d2 square theta 1 d square. Then kinetic energy of the translation of the third mass is going to be this big long expression, and I'll show it in just a second, this big long expression. And then kinetic energy for the rotation of the last mass is going to be this expression. Then we will have the expressions for the potential energies. These are going to be the expressions for the potential energies. And then we will have finally the equation for the Lagrangian. And this is the expression for the Lagrangian. Kinetic energy of translation of first mass, kinetic energy of translation of the first rotation first mass, kinetic energy of translation for the second mass, kinetic energy for the rotation of the second mass, then kinetic energy translation third mass, kinetic energy of the rotation of the third mass, potential energy for the first mass, potential energy for the second mass, and the potential energy for the third mass. And I'm going to paste this code again in the chat window. Run the code. So TH2, okay, there is an error somewhere. I will quickly check KER2, KER2, TH1D, KE3R. This is TH1. And the last part of the code is you have all the plotting. So I'm gonna paste it over here. And I'm gonna run the whole code. So, okay, here, run the whole code. And then it will run for some time, and then it will generate the plots. So I'm gonna, and if you look at the plots, one thing I want to tell you that this robot is unstable. And that's why when you look at the plots, you are going to see very large numbers on the velocities. So you can see the displacement of the first link, then the displacement of the second link, and the displacement of the third link. They are well within limits, but the velocities are super high. Okay, so I'm gonna type whole code again, complete code. So here is the first section of the code. I'm pasting the code in the chat window. This is the first section of the code. I'm gonna give you the second section of the code. This is the second section of the code. And let me give you the last section of the code. This is the last section of the code. And what I will do is I will upload all these codes for the cylinder rod and Rpr Robot dynamics in Canvas, so that you can look at the code and run those codes again on your own and compare and check your answers. Please understand, solving a rigid body dynamics problem in 3 dimensions is not a trivial task. It takes a lot of effort and a very systematic approach to solve the problem. So expect some struggle. So when you start working out the problems, initially the things may not work, the language may not be correct, the answers will not make sense, but you will have to gradually work through the problem and then find out the answers. Now I'm going to show you the plots again, and I just please confirm that you are getting plots which are similar to the plots I have shown over here. Fantastic. So now at this point, I would like to answer any questions that you may have. Please understand, the next quiz will include some of the calculations that we did in today's lesson. So you will have to solve complex dynamical problems for robots. So please go through this procedure step by step. look at the forward kinematics problem that we worked out in lesson 6 and review the notes and make sure that you understand the process of solving the problem. And at this point, I'm going to stop sharing. And if you have any questions, I would be happy to answer.